I'm Elliot. I'm from Chalk. I'm one of our co-founders, and I'm going to give a talk today about how we can accelerate plain old Python functions by transpiling them into SQL. As a little bit of background, the reason this is really interesting is for real-time machine learning use cases. For things like recommendation systems or fraud, you want to know what happens like just a few milliseconds ago, not like the last time your batch ran. So for example, if you're trying to do like credit card fraud, you want to know that like a credit card was just used in Ohio so that when you see a swipe in LA, you don't let that through. So there's kind of like two aspects to real-time machine learning in applications, and one is kind of how fresh your data is, like when was the last time that it was computed or pulled into the system, and the other is how fast can you serve it. And for a lot of these types of applications, we're seeing folks want things like 5 or 10 millisecond response times. Typically what this means is that companies will build kind of a bespoke solution when it comes to productionizing their models. Maybe in development, they're doing things in a notebook with like pandas or polars or DuckDB, but when they want to bring that to production and implement the same thing, they end up kind of re-implementing a lot of the same code, but integrating it with different data sources that are maybe more real-time or functions that run in the moment. So what is this kind of real-time machine learning? Well, what we see people doing is writing a lot of different types of functions to compute on data in that moment. So that might be, for example, expressions, things like you would see in a data frame expression, Python functions that just compute on other pieces of data, interactions with a database, sometimes a real-time database like a PostgreSDB or a DynamoDB or Redis, and like calls out to LLMs. So for example, if we wanted to run a query which was taking in like a review ID and asking for a normalized rating out of this, it might involve a lot of different computation that all needs to get strung together, not just one function that can run that. Like there might be a huge chain or data pipeline leading up to that moment. And doing this in batch, there are really good solutions for this, like a Snowflake or a Databricks. But if you want to run this at like 10,000 queries a second and see P90s of like 25 ms, you're going to have to start kind of re-implementing that code for that really specific type of a use case. So what we do is we query plan these queries in the same way that like a PostgreSDB would query plan, but where our functions or our tables are going to be a bunch of different types of things. Some of them are going to be SQL queries that federate out to existing databases. Some are going to be Python functions that run on top of that data, and some will be expressions. So it needs to be really declarative, just kind of easy to specify what this data schema is, and lead to really efficient compute, both for that real-time side as well as for when you want to backfill this same data. It all kind of starts by just laying out like the schema of your data, and we just do that with a Python class. We put this little decorator at features on top of it, and then all the annotations on that class will become the schema that we have. So for example, we'll say a transaction has some simple scalars like a total, an ID, a created at, date, time, for example. And some of our scalars are going to reference other classes. So for example, I'll say that user ID feature isn't just like an int, but it's actually pointing to the primary key on another class. And that defines our join condition between these two different classes. So I can affix that user annotation to the transaction because there's a foreign key to the user ID. And kind of on the other side, I can now say that a user has many transactions, or it has a data frame of transactions. Once you've got some stuff like this, you can start building expressions in terms of the schema. So I might say, for example, that like a transaction is expensive if the total is greater than 1,000. So there are a few different ways to then compute on this data, right? All we did so far was just kind of like lay out the data schema. We said, okay, we've got this schema for our users and for our transactions, but like, how do I actually hydrate those types of models, both in production as well as for those backfill use cases? And we'll look at kind of 3 different types of what we call resolvers. The first is going to be an expression, and you got a little preview of that with the is expensive piece. But you can start doing these over relationships too. So for example, if I wanted to compute the total spend for a given user, I might look at all their transactions. So that's that underscore.transactions there. And where the underscore is just kind of like referring to the class. So Python can't reference like itself. We'll just use an underscore to represent this. Go to the transactions, and then kind of for each transaction, we want to pull out the total column and compute the sum. And because we've written this as an expression, we can do it efficiently for one user at a time, or we can turn this into a computation on all of our users, for example. Or you could do a more complex expression. For example, if I wanted to compute the like maximum of the transactions by another column, I could do that. The second type of resolver that we see people write is Python. This is really great when you've got like complex logic that you want to codify as just a plain old function. When you want to integrate with a third-party client, like make an HTTP call to an existing external service or do something like run an LLM. These resolvers, you just put a little decorator on top of a plain Python function. So for example, in like a marketplace example, if I wanted to compute the discount percentage for a given user, I could take in any of those features from the user or any of the features that could be reached through a relationship. So for example, I might take in the user's total spend, their transaction count, their loyalty score through their rewards data, and pull that in as variables. And then inside the body of this Python function, I could write any plain logic that I wanted to. And we can use this anytime we need to compute the discount percentage. So if there's a request that requires knowing the discount percentage, we'll figure out how to solve for all the dependencies that are showing up here in the type signature. So we're really just using Python as a DSL to kind of like list out your data dependencies. So that would be kind of the second way. And then the third way to compute data would be via SQL. And we can reach out to these SQL databases in real time via these SQL resolvers, which are just files that end with the extension .chalk.sql. Now, at the top there's two really special comments. The first says that it resolves part of a given class, in this case a transaction. And what that means is that all of the target expressions like the ID, the description, the receipt ID should line up with features on that transaction class. And so if we need to go get data from one of those, we can. And we can do it in different contexts from different data sources. So for example, if you wanted to offline, like grab transaction data from BigQuery, you could write one query and do a different one for kind of running against production, against like a Postgres system. At runtime, or at this backfill time, we'll push down filters and aggregations and projections into these SQL queries, so you're not overfetching your data or pulling a bunch of unnecessary rows. You're just getting the ones that you're interested in. And inside these query plans, we can just treat this as like one of those UDFs. Finally, you can also skip computation of certain parts of this graph. So for example, if you have a feature that's really expensive to compute, you can specify the maximum age you're willing to let that feature get to before you want to recompute it with this concept of max staleness. So for example, if a transaction had a fraud score and you said, well, that fraud score, once you've computed it, is valid for a day, but after that it needs to be recomputed, we'll first kind of look for that fraud score in a cache, and then if not, kind of fall back to running the rest of the plan. So mostly what I want to talk to you about today is how we can run Python really, really efficiently inside these plans by converting it into basically SQL expressions. Really taking Python and treating it as a DSL all the way down to the language and the runtime. So why are we doing this? Well, Python's really flexible and people love writing it. It's really good for expressing certain concepts. But it can be very, very slow to run. And there are a few good reasons for this. So one is there's this GIL, which I'm sure you're all aware of, and means we can't really get good parallelism. It has dynamic types that are and really heavy object representation, and it's all per row execution. So you can't use techniques like SIMD in order to accelerate these backfills or even real-time compute in cases where you have a lot of rows coming in and you want to compute the same function on all of those rows. So can we just turn this Python into SQL? And we can. So we need a SQL engine first up, and the one that we use is called Velox. It's an open source project started by Facebook in 2020 that we're big contributors to. And it was really built for those high throughput types of use cases. Like it's really a competitor to Spark that Facebook uses internally for all of its analytics queries. And what we do is maintain a fork of this, which is really built for low latency queries, and lets us unify these online and offline types of expressions. So for example, in the offline side, for training historical data, you're really interested in like huge cardinality data sets, certainly over 100,000 rows, but maybe billions or trillions of rows. The request wait rate is like, on some cron schedule, or it's like when a person runs a job. And it's really built for larger than memory workflows. So for example, you might want to spill the disk or run this across many, many machines. And this is really like the purview of tools like Databricks, like Snowflake. On the online side, however, we've got a totally different set of requirements. Like we want to run on typically one row, but it's coming into us at like 10,000 or 100,000 queries per second. And our latency budgets are something like 10 milliseconds. And we really care about how can we minimize the CPU percentage so we can get like efficient utilization of the machines that are doing this traffic serving. And so for the online case, we can sub out some of the operators that Velox uses and, for example, say like, well, we don't ever want to spill the disk if we're running in an online query, and so we can avoid a lot of expensive checks. And what this lets us do by kind of like just using Velox with different styles of operators in the online and offline context is have the same query planner, the same resolvers, the same functions, so that you don't end up with drift when you implement something when you're training a model and when you actually want to go to productionize that model. It also leads to a really great developer experience. So data scientists can just like write out what they want to do in a notebook, and when it comes time to take it to production, it doesn't mean rewriting everything in order to get that live. So we kind of eliminate this concept of like having data drift between these two different implementations. Now, one of the thing I'm really here to talk to you about today is how we can take Python UDFs and turn them into Velox expressions. In this query, for example, we're running like 18 chalk expressions, like 9 SQL resolvers, 5 Python resolvers, 4 online store lookups, or just kind of like cache lookups. And sometimes this is kind of like this is a little bit of a toy example. We see people who want to run something like 2,000 functions at the time of inference and do it all in like 40 milliseconds, especially in the anti-fraud space. So what we do is treat each of these Python functions, expressions, and SQL queries as a user-defined function from the perspective of Velox and put it into a query plan. And then we rewrite that query plan to be as efficient as possible. So when we take this kind of like simple graph and we expand it to see all the underlying SQL operators, we'll see a plan that looks something like this. And in there are the things you'd expect to see from a SQL engine, like projects, joins, filters, uniques, for example. So Python UDFs can actually be turned into these expressions as well. And we do this by what we call our symbolic Python interpreter. So what we found in production is that like a lot of Python functions are actually not too complex, right? They're like things like I want to compute the total of a transaction by looking at like the subtotal, maybe a discount that we're applying, some like local sales tax, and whether or not even the transaction was taxable. So like taking this example, which we're going to dive into and look at how we kind of turn to an expression, we might like look at the discount, and if it's not none, then first up we'll say, well, you take the discount off the subtotal, but it's not going to be a free transaction. You're not going to get money back in order to buy something, so we'll take the max of that in 0. And then if it's not taxable or if the tax rate is none, we'll return the subtotal, and kind of finally we'll like increase the amount of the subtotal by multiplying it by the tax rate. So that's kind of the Python function we want to look at and like turn into SQL. Now, you could write this in SQL, right? Like we could all figure out like how to write this as a case statement with some like nested stuff in there, but maybe as your Python function gets larger, or it's just kind of easier and more natural to like write this as a plain Python function and like unit test it. So what we'll do is take this Python resolver and at plan time, figure out if we can turn it into an expression. And this lets us avoid running Python entirely. So we're never going to run Python. We're never going to acquire the GIL. And we have, what we'll do is like basically these Python functions, because they express their data dependencies in terms of these feature classes, they have a really strict schema. Under the hood, we're using Arrow for all of this. Velox has its own types, but they're easily convertible to and from Arrow. And so we'll take the Velox columns, which are kind of like the inputs to our function. We'll turn them into Arrow data, or record batches. We'll then run that through this like Python, or this interpreted Python, convert it back into, which will output Arrow, and then put it back into Velox. And you know, of course, if we can't do this, like we don't have to have 100% coverage on the language. We can always fall back to running Python through like some subprocesses. So we're going to walk through that example that we looked at around the subtotals and see how this gets converted into an expression. So initially, the kind of like underlying type here is going to be this symbolic value. And a symbolic value is really just a Python type and a Velox expression. So initially, that just means it's all of our input variables to our function. And that's going to be what we call our environment, which is just kind of like the state of the program. So initially, right, when we're thinking about this Python function, it takes these 4 input variables, which are the discount, the subtotal, whether or not it's taxable, and the tax rate. And we have those as Velox columns here called, you know, D, S, I, and T. And we know they're Python types, like most of them are floats and one of them is a nullable float. And what we'll do is kind of keep updating that environment every time a new function runs. So for example, one of the first operations that we do inside that Python function is we take the subtotal and we subtract from it the discount. Well, the subtotal is kind of known in this Python environment as a column in the Velox table with the column name S. And the discount is another column with the column name D. We know the types for these two things. And so we can just delegate that function to the built-in subtraction operation and say that the resulting type is also a float, kind of just implementing like a little type checking as we go. We could then store that as a new variable in our environment if it was assigned to a variable, or we can kind of update existing ones. So looking at like a slightly more complex example, right? That was just kind of subtraction. We could look at how you might take the subtotal and set it to the maximum of the subtotal less the discount and 0. So really what we're going to do is we're going to take our initial environment, and that's that piece that's on the left, and we're going to see, well, we need to update subtotal, but subtotal already has some assignment. In the beginning of the function, it's just a column, but as we go, it'll keep updating. And what we'll do is set the subtotal equal to the maximum of the existing environment's subtotal, which is this DEF, minus whatever the discount function is, and that's like that ABC, and 0. So we've kind of understand that like Python's built-in max is going to map to some Velox function for max. And we know that the inputs to this can kind of recursively can be computed as Velox expressions as well, and that subtotal will then update its type to be a new Python type, although here it still maintains float. We can do a similar thing for conditionals. Python, of course, has ifs and elses in it. And what we'll do is just compute the condition itself as an expression, and then we'll compute the if true branch of the expression and the if false branch of the expression. And so this leads to two different environments. Like on the if true side, we're kind of updating it, as we just saw a second ago, where we like transferred from the left-hand side to the right-hand side. We'll do something really similar for these conditions. We'll compute the if true version of the environment and the if false version of the environment and the condition. And the result of that is going to be a composite environment where for each of the variables that should appear at the end of this if statement are set by checking that same condition. So we'd say, well, the discount in the if true environment is ABC, and the discount in the if false environment is MNO. And so we'll say that the discount after running the if statement is going to be if C ABC, else MNO. And you do that for basically all of these, and if you have some which didn't participate in like either the if true or the if false environment, then you can just assign them to like whatever they were at the beginning of the function. You can do a similar kind of treatment for early returns. So basically for all of these environments, we're going to be tracking whether or not there was an early return condition. And so we'll have some expressions of maps from basically saying like, well, if, in this case, GHI is true, then this end function is going to return MNO. And we can give this a similar treatment for like figuring out what the return of this function is going to be, where if any of those conditions trigger, then we want to set that to be the output column of this expression. So what does this look like kind of like in the end, or like after you go through the process of converting that whole function? Well, the function, which on the left here, ends up becoming this expression. So you've got at the top, like there's just going to be one kind of tree, like we're going to have one node at the root here. And all of the leaves are going to be our potential return values. So like first we're saying, well, if not discount or discount is none, we've got one expression which is going to like be the nested version of kind of like inlining all of the compute which could come after. So you'll have these really nested trees as a result of doing this transpilation, and then we can apply rewrites to the top of it to kind of prove that certain conditions are true. So if you've already checked a condition like in some walk up to the root from where you sit, and your expression is like trivially true, you don't need to like recompute it. You can just assume that it's held through that branch of logic. So what this really means is we've got Python as like a domain-specific language for writing Python expressions. You can write Python, and there's kind of no consequence to it. Like it'll run just as fast as if you wrote like a BigQuery query and ran it against BigQuery when it comes to a backfill. Or in real time, it'll run entirely in C++, and you'll never ever require the GIL. And we don't have to, I mentioned this earlier, but we don't have to have a perfect map of all possible Python. We can always fall back to running Python when we need to. And this has kind of like gotten more sophisticated than you might imagine. Like we've gone through some of the simple like if conditions and else conditions, but we actually support like for loops and arrays and like mutations of data and dictionaries. You can also support like random Python libraries. So we support like hashlib and statistics and NumPy functions. And as long as we can map them into a Velox UDF or like a function in C++, we can just take the Python expression, turn it into the symbolic value, which is that combination of the Velox expression and the Python type. And then, of course, there are certain times where you might not want to do this, or pathological cases. And so that, you want to track as you're doing this transpilation, like some gas limit. When that gas limit expires, you want to kind of give up and say, fine, we're just going to run this as Python. So that's kind of our talk about Chalk and Velox and how you can run expressions. But I would love to take any questions.
All right, thank you very much. Folks, we have like the thread on the track machine learning, data science, and explainable AI. If you can post your questions there, or if now someone has it on the room, I can just hand the mic very quickly. Over there, we have one.
Easier than pulling up my laptop. Yeah, so I was curious, so you talked about how it converts to Velox, but then you talked a little bit earlier about some of the other backends like executing on Snowflake and things like that. So how are you converting from Velox to the actual SQL dialects?
Yeah, absolutely. So I'm going to pull up one of these query plans here. But like Velox is a SQL execution engine, basically, and we're only doing these in Velox. So, I mean, Snowflake and Velox and BigQuery are all going to have like similar kinds of functions, but they've got like a slightly different library. Like maybe Snowflake is using like HLL plus, and like BigQuery is using like some other thing for its like implementation of a function. And so these transpilations only happen in Velox. When we call out to SQL, it's more like what's going on in this bottom left corner here, where part of your query is mapping into a feature class by way of one of these SQL resolvers. So this could be talking to BigQuery or to Snowflake. And internal in the plan, we might run a query against BigQuery and like push down a filter into it in order to get some like in memory or on disk representation of the like transaction feature class. But then if you wanted to compute a Python function in there, we would do that as a new column in the table. Does that answer your question, or is that what you're thinking about? Okay, yeah.
So for the actual feature compute side, that's all the Velox.
Yeah, it would be challenging to maintain like for like a lot of different databases.
Do we have any other questions? All right.
Thank you. Great talk. I apologize if I missed this. Do you have like a visual profiler so that I can answer the question for myself? Did this end up falling back to Python, similar to like what Python has?
Yeah, absolutely. So let's see if, yeah, cool. This would be like one of those query plans, like in the query plan visualizer here. And you can see when we were able to compute it, you have this like accelerated Python label here. And this was the like input function. It was kind of simply saying like, well, given an email, I know how to compute an email username. Like first I do the obvious thing, I'd split it on the @ sign and take that first part. And then if Gmail's in there, well, they let you have these special rules where you can put a plus sign and have like an unlimited number of aliases here. And finally, like no matter what, I'm going to lowercase that. So in the every time you run a query, it's going to output a query plan, which will tell you like all of the graph that needed to run. And this particular node, you can see, got converted into an expression. So it was like, well, lowercase everything, and like here's our if check for if Gmail's in there. And if so, I've got this more complex expression, which is going to say like, oh, like replace, do some string replace a couple different times for plus and for dots. And otherwise, it's like this relatively simple expression. So you can see kind of in the web like when we were able to do that, and then there might be certain times where like, oh, we don't support like the JSON module, like JSON.loads, and so this didn't get converted or transpiled. Yeah.
Do we have time for maybe one more question? Do we have any other questions? All right, another one of them. In the meantime, I noticed that your slides at the top have some, what it looks like GitHub handles next to the thing, and they're all changed.
Oh, yeah.
Yeah.
A bunch of people helped out with this. So Elva sitting back there is our amazing developer advocate, made most of these slides. There's another guy, Nathan, who did the work on the symbolic Python interpreter, and I'm just here to talk about it.
Okay, yeah. So I guess one more question is, I saw in the docs and like from knowing Chuck a bit before, like that you have online features as well. So
Yeah.
for the online features, are they kind of computed the same way as the batch features all through Velox, or is there any difference for how you're doing that?
Yeah, so the query planner is still Velox. We're going to sub out different operators. So like in the offline case, you want to spill the disk, right? If the data is too big, you don't want to just like give up and You want to start writing things like out to disk and stream the results through. You might also want to like partition it on a bunch of different machines and run it that way. Those would be inappropriate operators if you're trying to maintain like a 7 millisecond end-to-end response time from the perspective of the client. So it's the same like query execution engine, but you might say like, okay, you can use this spill to disk like join node if you're doing a batch compute, but you're not allowed to use that node. That's never going to get injected into the plan if you're like trying to do something where you have like any kind of latency budget. So it's going to use the same plan. And these online resolvers, which maybe you're thinking about too, where they have these little decorators, really that just means they can run online or in batch. So we're going to take these same functions, and because Velox is converting these to expressions, it's like not a big deal to apply it to 100 million rows or to like one row. But even for that online use case, it's going to operate much faster than like actually running Python and much more stable. You're going to kind of remove like bad P99 spikes because you're subject to like Python's GIL and like when it might garbage collect or something like that.
Yeah. Give me a sec, so I just get you there.
Sorry, I'm completely new. Thank you. I just was asking, why would it run faster than Python?
Yeah, absolutely. Well, Python's like a scripting language, which is really nice to write and really convenient to write. But there are a couple things that make it kind of like fundamentally slow. So one of them is this thing called the global interpreter lock, which basically means your Python's going to run kind of like single-threaded. And Python's done some things to try to get around this. And in recent releases, there's a way that you can run GIL-free for certain functions. But even then, you're subject to the kind of type system of Python. Like Python has a really heavy runtime. It has dynamic types, right? You can have something be like a string or an int, and you can like is-instance it. And it has what's called a heavy object representation of those types. And it's also really per row execution, right? Like if you want to do an operation on a bunch of rows in Python, you like write a for loop over them. That's very different than something like executing with SIMD, which is like same instruction, multiple data, something like you'd run on a GPU where you might say, hey, I've got this, like I want to perform addition on like all of these rows right now. So it's the same instruction, but on many different rows. And if you kind of have a more rigid type system, and you can express your computation as more of like an algebra and less of like a imperative, like run this line of code and then run this line of code and like see what happens. It's a lot easier to accelerate it. Yeah, exactly. So what we're doing is saying like, forget the Python types. Like we're going to figure out from the type signature what the arrow representation of these types are. And we're going to say, we're assuming that this is a float. And it's going to be like a float 64, not like some dynamic, infinitely large float like Python might treat it. And then we're going to turn this into one of those expressions, like a SQL expression. So you probably notice this kind of like speed difference when you run something on BigQuery and you like run a huge computation. You add a ton of numbers together, and then you try to go on your computer and run like a for loop over like just 1 million numbers. Like, wow, this feels like 10,000 times slower or something like that. That's because BigQuery has all those advantages of its language being a lot simpler and its types being a lot more constrained, so that it can accelerate this compute both by running it on multiple machines and even taking advantage of the like single machine and some of the cool CPU instructions.
Well, let's thank our speaker. There's like one comment in the Slack thread that says introduce interesting use case and talk. Thank you very much. And some folks that kind of gave it a thumbs up. So awesome. If you have any more questions, you can put it on that thread, and then our speaker later on can go and check it out, or like Fan can probably outside. Let's thank our speaker once more.
Thank you all.